Today, I would like to talk about the possibility of simulating the Josephson junction on a SPICE software. And unfortunately, the only SPICE that supports them is WRSpice. So we're gonna need that, and I'm gonna take you through the steps of installation also of this software, because it's not as straightforward as it may seem. Yeah, and then I will. Before that, I will talk about maybe very, very briefly about the physical background of the situation we are trying to model. Yeah, and then how to deal with the WRSpice netlist, and how to export files and make use of them, for example, by doing some animations and using them in Python. So firstly, I would like to introduce you to the situation, to the physical situation that we're dealing with. So basically, Josephson junction is two pieces of a superconductor and a semiconductor or piece of another material sandwiched between them. So this is, let's say in our case, semiconductor, and these are superconducting pieces. This one as well, yeah. Okay. Between these two pieces of superconductor, there is there is currents freely circulating in both of them, and at the junction there is created an accumulation of electric charge, which causes Josephson voltage right here. And this is the thing that we will be trying to model. And also there is some communication between the two. There is some current between the two, and this will be called I0. So this is the situation even without applying an input current. Yeah, but let's suppose we apply some input current from this side here, and let's say it will be a square impulse like this. And this provokes two responses across the Josephson junction. First of all, we get the voltage response, which when the precisely at the moment when the current jumps, we get a very short impulse of voltage across the junction. So this is the first response. And the other response is sorry. The other response is phase response of this superconducting current. So if we have phase, let's say phi of the current, and we apply this voltage, apply this voltage, this current impulse I. At this moment, the phase begins to shift, and by the time the impulse is over, I mean, by the time the whole impulse is over, we should experience the change of 2 pi in the entire period of a phase. And yeah, so the current across the junction is proportional. Is dependent on 3 variables. First of all, it is this amplitude I0 that we had here, and this phase phi. Then we have to account for some built-in capacitance of the junction. So we have another term. And there's also some ohmic current. Yeah, but the most important dependence here is the dependence of the rate of change of the phase across the junction in the of the superconducting current, and it is
phase difference, Radoslaw, phase difference.
Yes.
What you call phase is a phase difference between superconductor A and B, right?
Yes. So the rate of change of this phase difference is proportional to the voltage and anti-proportional to the flux quantum. And, okay, maybe you of course you remember from Faraday's law that voltage is simply rate of change of the flux. So the flux quantum that we have here, because in this situation the flux is quantized, is this voltage response that we get here is integral over time. So and this is the flux quantum. So the phase is proportional to that. I mean, the phase change is proportional to that. Now, okay.
Sorry, Radoslaw. Thank you for this introductory presentation. My question is: these phase differences, is it something that we have to kind of like put ad hoc in order to understand the phenomenology of the Josephson junction, or is it something that we can, from first principles, let's say, if we apply electromagnetics description of the materials, that the Maxwell equations, let's say, would produce this phase difference? Do you understand my question? Is this?
Yeah, I do. If you can derive this from
microscopically, yes.
Perhaps I can answer this question. Yeah. So basically, what you have is you have a Bose-Einstein condensation in superconductor A and B. So superconductivity is like first stage of Bose-Einstein condensation. So the whole system, the superconductor, is parameterized by superconducting order parameter, which is square root of density of Cooper pairs times E times phase. And this phase, the global phase in a sense. So it's like phase of macroscopic wave function. And when we talk about phase difference, it's about a phase difference of 2 macroscopic wave functions. Here is on the top and on the bottom. So and this phase difference is induced by vector potential, by imprint of vector potential, as in Aharonov-Bohm effect. So in very real way, the current is run here by by controlling phase difference or by inducing certain vector potential across the system. So you can say that current cannot flow if there is no vector potential. So this is like London relation. In London relation, you have electrical current density proportional to vector potential, while in standard ohmic law, you have current density proportional to electric field. And then actually there is a mapping from ohmic law to London law, because if you simply go with a Drude model with relaxation time going to plus infinity, which means very ordered system, then from essence from ohmic equations you can go into London equation by time integration essentially. So you can play such tricks, since simply saying is electric field is one of the terms of electric field is minus d over dt with on the vector potential. So here as in regards to this model, so what Radoslaw is describing is two-fluid model. So two-fluid model is a phenomenology which is very effective in the system description, and this phenomenology is valid for superconductor or superfluid. And in this phenomenology, you have a preassumption of coexistence of two types of liquids. A liquid of Cooper pairs, which is like quasi-bosons, in a sense bosons, let's say, that obey Bose-Einstein statistics, and unpaired electrons, which cause resistance. So you have superfluid liquid and normal liquid, which causes dissipation. And here, the superfluid liquid is accounted by I0 sign of phase difference, while two other components characterize the dissipative liquid. So there is also associated RLC circuit, the circuit with that equation. So I hope that I have somehow answered your question. Right?
Thank you, Christoph.
Okay. So now I would like to introduce some symbols convention to avoid further confusion, because first of all, this is the symbol of Josephson junction, the most basic one. However, if we consider a perfect Josephson junction without capacitance, no resistance, then we can call it, like, we can add a subscript P, like here. But in a real Josephson junction, we of course have capacitance and resistance. Let's call it Rn, like normal resistance, and also a perfect Josephson junction. So this is a model of a real Josephson junction. This can be drawn simply like this. And in our situation, we add to this real Josephson junction another resistor. So we build something like this. We have real Josephson junction and resistance here. We call it RS, like shunting resistance, because we want to be able to modulate this voltage response by changing this resistance. And this resistance can be modulated by biasing current from this side. So on yet another slide, I will present you the most basic parameter that we use for modulating the voltage response of the Josephson junction. So as I said before, the voltage response looks something like this usually, and this is the situation for beta, well around around 1, let's say. So, I mean, sorry, I haven't introduced the beta. Okay, so the most basic parameter that we use for modulating this voltage response is parameter beta, which is proportional to the capacitance and to the square of the resistance. And as it has been said, the resistance can be modulated by biasing current. Okay. Okay, so this is the situation where beta is around 1, let's say. When we increase this beta, for example, we make it, we add, change the.
Radoslaw, could you
yes?
Could you write down the value of flux quanta here?
Of course, yes. I should have done
just
it before.
by formula, just refresh us. What was the
cool.
Formula.
So the flux quantum is equal to h by two charges of divided by 2. Sorry, it's not h bar. It's simply h by 2 charges of electron. So
thanks.
This is yes. Yeah. So this shape of voltage response would be equivalent to parameter beta of more or less 1. Now, if we want to increase the resistivity, and we do that by increasing the biasing current, we would get more oscillation. We would get something like this, and it would take longer to stabilize. So this would be for beta larger than 1. And if we reduce the resistivity, we would get beta lower than 1. Yeah, so we would get only 1 peak right here. So this is for lower than 1.
So how you call it? Beta is Mach-Camber parameter, right?
Yes.
Okay. Good. Go ahead.
And this property is used to build more complex structures where we can regulate the transmission or we can cause transmission or blockage of this flux quantum simply by changing this biasing current here. So if we have some current I0, the superconducting current across the junction, if we want to allow transmission of this, I mean, if we want to provoke this voltage response and hence the change of phase by 2 pi and hence transmission of the flux quantum, then we would have to have current higher than this I0. Yeah, so here we have our flux quantum. And we can block it or allow for transmission, and this can be used as a part of a logical circuit, therefore, because the presence of the flux quantum is can be considered logical 1 and the absence logical 0. Now, so
one more comment, Radoslaw.
Yes?
Radoslaw. So there is existence of inductance. What does it represent here? Inductance. Ideal inductance is represented by what material? by superconductor. So in a very real way, the superconductor is ideal inductance. It's just a comment to this picture. So this inductance, presence of inductance, which is pointed out here, is nothing else as simply the strip, the superconducting strip, right? And then that's all right. Yeah, that's just a comment. Please go ahead.
Okay. So I don't want to dwell too much on the physical part, because I would like to show you how to simulate the Josephson junctions. And as I said, the installation of the software is not as straightforward as we would want it to be, because first we have to install MI system sys2, which is something like, which is a plugin, or what do you call it, an additional utility for the PowerShell in Windows. And I put all the links here because I may later share this presentation to you, and with that it would be much easier, because finding this information on the internet is not very well. It would take some time to figure out how to install all this stuff. So first of all, we have to add some.
Could you please magnify your slide, because it's a little bit visible. Please go to full screen mode.
Okay. Okay. Then we can install we simply download the installer files of XIC tools, which is basically the graphical interface for WRSpice, but it's not a graphical interface like in LT-Spice. It means that it doesn't plot you any schematics. It just can plot you the outcomes, the graphs of the quantities you want. But it's not. You cannot see schematics with it. So we have to download it, and then once you download it, you open the dialog window, and you put some additional commands. They're all listed in this instruction on GitHub. You need that because it installs some additional utilities necessary for this to work. And once it's done, you can find it under this icon. And you're free to input your netlist into the program. But this here is pretty straightforward. I mean, you don't have to know any commands from it for this dialog window, because everything is defined in the netlist. Every instruction, whether to run simulation or not, every parameter of the simulation is defined inside the netlist. So maybe I would like to first, before everything, I would like to show you the structure of a exemplary netlist, and that's why I clicked my full screen for a moment. I wanted to. Okay, maybe I can magnify that for. Okay. The only thing we define in the netlist is the list of devices. So we name them. If we we have to remember about the convention that if we start the name from like large L, it will be inductance, and the program will detect this as such, as inductance. The further two numbers are the two nodes that it's connected to. This is like positively polarized node. This is negative. So this is the node with higher potential, lower potential, and then we define the value. So this is quite straightforward for resistors, capacitances, and inductors. For Josephson junctions, it is a bit more complicated because, okay, here we put the name. If it's if we want to put a device that it's not a standard model of this program, if it's not inductance, capacitance, resistor, we have to put B in front of it. And then we, of course, define the two polarized nodes that it's connected to. But we also have to, in the case of Josephson junctions, we have to define additional node, which will model our phase response. So this is our node, let's say in between these two. And apart from that, we have to define a model. So before, at the very beginning, or actually in any point of the list, we have to define the model of the Josephson junction. So here we put the name of it. We have to use the keyword model, the name of it. Then we have to tell it that it has to be a Josephson junction. So it is JJ. And now level, this is a parameter that tells the program which mathematical model to use for calculation. I mean, the most simple one, and we don't need anything more complicated than that for now. And then we define the capacitance and normal resistance, which are these parameter of the real Josephson junctions that we were talking about.
Rado, can you explain what do you mean by level 1 mathematical model? This
is information for the program, what numerical methods to use for simulation, basically. So it's not.
It's numerical analysis, like what algorithms you're going to use for matrix inversion or solving linear equations. This type of mathematical.
Yes.
Okay. And my second question is, this is all in Python, right?
This is this is some text editor. So this file has an extension SIR, which is like typical WRSpice extension.
So in terms of the editor, you use VIM. What kind of typing editor do you use when you type all that and you program all that?
Actually, I'm displaying that in, of course, in WS Code. Okay. I mean, in VS Code, sorry, but I actually did this file in Notebook. I wrote some scripts that generate this file automatically from Python, but you can do that in Notebook, really. If you don't have really huge model with a lot of hundreds of nodes, then you can do it by hand, and any text editor will be good. You just have to remember that it cannot be saved in TXT extension. As your notebook sometimes will try to force you to, but you have to save it under this extension, and it will be good enough. But.
And also at this level,
yes,
basically you can write down pretty much anything. Are there any physics constraints? Like basically they can tell you, oh no, you cannot put like are there any physics constraints in terms of what kind of networks you can create?
You can create.
Is that part of SPICE, or?
Yes, it is.
Okay, okay.
Yeah. So if you want to, I of course included the website where you can see the full instruction and read read all the. I mean, because we cannot cover every single device today, and
can you type it on the chat so we can access?
Of course, we can. That's okay. So I will close the full screen and type it. So this is the instruction where you can check which parameter is responsible for what, and what is the structure of defining certain device that you want. What I can tell you today is only where to put these parameters. I mean, first you define the one node, second node, the phase node, and then you define model, and then some additional parameters. If you want more details, it's all in the instruction. But another important thing I wanted to talk about was, so, okay, this is still about parameters. This ICS parameter is a critical current, which is exactly this current that, this is, let's say, I0, the current that, the current has to be higher than critical current for allowing transmission, for allowing this.
Radoslaw, please go to full screen mode, please.
Yes, but I have, from time to time I have to close it and show it
because it's very small. The font is small.
Okay. But before showing,
let me say for the attendees, if Radoslaw is easier for you to stay in the mode you are on, not the full screen, we can go to the three dots on our Zoom as attendees, and we can change our screen resolution to 100%, and then it will be more clear for us without Radoslaw having to change on his home computer. If that's easier for you, Radoslaw, I would prefer that. I would prefer you stay in the current mode, and then we change from fit to screen to 100%, and then it's very clear and very visible. Just a suggestion.
Okay. Another thing that I wanted to talk about is plotting and exporting data. So if we have this netlist right here, at some point we have to, if we want any plots, we have to declare simulation, which is like this keyword, control, run, and we can this function, I mean this keyword plot, means that we want to plot it right away in WRSpice interface. But yeah, it's usually very poor quality. So well, if you want to use it, it's very cool to see the data ad hoc and like yeah, it's very quick. But if there's another option to also save this data to a file, and we have to use function write. Then we have to name write the name of the file. Let's say, for example, it has to go with the extension, and then we put the same thing. I mean the number of nodes that we want to simulate. Here it means that we simulate the voltage across the nodes 71 and 7, voltage across 5 and 9, and voltage across the 10th node. But another thing is this works perfectly well for simulation of voltage. However, if we want to plot, or save to a file also the simulation of current, we cannot do it by specifying the nodes. So we would have to tell it to plot I, but of course plotting the current across node 7, for example, doesn't make much sense, because let's say this node splits into two branches. The current on left branch is different than current on the right branch. So we have to specify the name of the device that we want to plot. And as in my case, I will later show you the animation. I wanted to plot the input current. So we have to resort to a trick here, because there is no device at the input. And so there is a way to work around that. I declared here, okay, I wanted to see what's the current through the branch from 0, which means basically ground, to node 1. That's what I wanted to plot, the input current. But we have to specify the device. So here I created some dummy generator, which doesn't generate anything. This is the voltage that it generates. It's always 0. And I created a dummy node. So that now this input current this current source spans from from ground to our dummy node. Then we put our dummy generator from this node to 1, and we can plot the input current through this device, through this dummy generator. Okay. And the result of this simulation is a bit messy. I mean, it has a lot of metadata. It has a lot of tags and information we don't need. So we have to somehow change it to tabular form, or any form that is useful to us. So for that, I created a Python function that takes in this simulation file, parses it, modifies it, and spits out the data. And the results for such a simulation can be from such a simulation can be later processed, and it can be treated as vectors. You can make animations out of it. And I wanted to show you a couple results. For example, for the circuit that I show you at the beginning, this basic cell that can model transmission of the flux quantum. This is the animation I got. So I decided to plot the input current through node X, which is here. So this is our, let's say, we had to put the simulation across this device, this dummy generator, and I wanted to plot input through this through this node, through this other dummy generator, and we can choose some. We can choose some Josephson junction and see the phase response to these current impulses. And this is the result that we get. Now, we can investigate what happens if we change, for example, okay, I will go to full screen now to show you how it's done here. Okay. So if we define the nodes that we want to plot in our netlist, this is the result for the most basic setting, and we can see what happens if we change the resistances. For example, here all the resistances are increased to 5, and we can see the change. The change in the voltage response, and all the resistances are reduced here, and we can see it right away. These are the plots taken from WRSpice interface. Yeah, so we can also see how it actually changes. I mean, decreasing the resistance causes, of course, that this voltage response is much weaker. So we would expect much slower phase response, and this is what we get on this graph. However, increasing this voltage causes more oscillation and more aggressive change in the phase, and we can observe it on this plot. I actually did a lot of a huge side task of trying to plot the schematic out of the netlist. So it was a lot of things to do, but the oscillations that we can see here are voltage responses across these nodes. So, for example, this is voltage across 4 and 3, and it's plotted here. This is voltage across 5 and 4, and it oscillates like this. This is voltage across 6 and 5, and so on. So this is the result of my work in this software simulator of Josephson junctions, and I think that I think that is everything I prepared for today. I wanted to show you something like a bit bigger structure. Unfortunately, the files were left on my other computer, but this is the behavior of a basic cell that we introduced at the beginning of this lecture, and we can see everything graphically, how it changes. Yeah. So thank you.
Thank you, Rado. I wanted to ask, can you play with different, let's say, materials, different, like, let's say, superconducting materials, make a Josephson junction from different underlying materials, superconducting materials?
You can certainly change. As I said, a different material. You cannot tell it which material do you use. It doesn't have. It's not built in, but you have to define.
I think partly you can. Radoslaw, can you come to this?
Partly, yes. You can define this parameter. You can define parameters. You can define normal resistance. You can define critical current. You can define the capacitance.
Can you come back to
there's
this slide? Can you come back to the slide where there were level 1 parameters? Can you come back to this slide?
It was actually here, yes.
Yes, so here Rn stands for this resistance that is proportional to the size.
Normal resistance, yes.
It's a resistance of Josephson junction in normal state, more exactly, right? So when it crosses, when it transfers from superconducting to normal state, since this is a sandwich, superconductor, insulator, superconductor, or some sort of sandwich, this sandwich has a certain resistance. And then the level 1 probably is associated with certain technological process, because you are talking most likely about rapid single quantum flux electronics, right? This is what you do. You refer to it.
Yes. Well, actually, it's it's
I would say
single flux, but I wanted to the name of this technology is called resistively capacitively shunted Josephson junction, because
it's not the name of technology, it's the name of model. Yeah, it stands RTSK stands. But still, what I'm saying is, because you are very strongly referring to the concept of rapid single quantum flux electronics, and simply saying this rapid single quantum flux electronics allows to create highly integrated circuits made from Josephson junctions. And there you have certain technological processes, and I assume level 1 is just certain type of process that generates a certain size of Josephson junction. So it's simply associated with technological process, but since junctions are repetitive in that way, so it is directly associated with critical current. So in very real way, level 1 is associated with I0 value from your previous slide, right? There was I0 times sine difference of phases, right? So that's it. Yes, this model is applicable to BCS superconductors in general. So like aluminum, niobium nitride. So most superconductors that are categorized as low temperature superconductors can be expressed by RCSJ model. So, but those parameters, so are combination of geometry and material. So that's the answer to the question, right?
Okay, so thank you for clarifying.
Can you come back? Can you come to this paper which I attached to this chat? There's a paper.
We'll take a look.
Yeah, a little bit magnify. So there is this beta parameter better described. Can you just McCumber parameter? So this is this relations which you have here, and here it's point it's number 2. So this is this parameter, right?
Yes. Okay.
And then go down, and then you have 2 regimes go down. So I mean, you're supposed to have overdamped regime and damped regime. So you have second order differential equations. Yes, this one. No, go back to the line 4.
Line 4. Where is it?
It's that's 3 and 4, right, and 5. So you have pointed out today the equation number 3, right? So this is what you have written, right?
Yes, I have. The case where beta.
Go ahead.
The case where beta were smaller than 1 is the overdamped case, and when beta is higher than 1, it's underdamped. So
yeah, but the methodology is by going from equation 3 to equation 4, and then to equation 5. Then it's natural to have beta c, which is this parameter which you described, And there are two limits of it. First, when beta is close to one, very big or very small, right?
Mhm.
And also can be close to 1. So this is how it comes out. And then maybe can you go to equation 5 still? 5 equation number 5. Yeah, so what type of equation is that? Can you make any comments just by looking on this equation? Is this equation similar to other equations you know?
It looks like damped, damped pendulum.
Well, it can be. It's so let's say indeed it is. It's damped nonlinear pendulum, and the external force is I. So global current, which is sent via these junctions, stands for it's like external force, and then you have certain terms. Yeah, so that's how it is. And yeah, could you proceed with this paper? Just yes, make it smaller, the zoom size, and go further. There is a table of comparison. Yes, this table.
Okay.
Yeah, can you make it? Yeah, just go a little bit down so we can see the whole table on the screen. All right, and then please just have this comparison, and maybe you can make some comment on that. Yeah, also about these analogies. So phase difference in Josephson junction between left and right superconductor can be mapped to position in a nonlinear pendulum, like a position, like angle or x coordinate, right? Then you see external supplied current. So total current which you send is visible as external force or external torque, which is here. Then the capacitance times h bar over 2e is a momentum. It corresponds to momentum in classical pendulum, right? So and then the conductance, or in your case, is 1 over r, because you have not used G, big G, but you have used 1 over r. So G times h bar over 2e is a damping coefficient, right? And then from standard pendulum theory, and also maybe one more comment, if you have very small phase difference across Josephson junction, sign of small value is a small value, right? If you have a small argument of sine function. So in that way, you can linearize this equation. You can linearize. And then, so first thing which you can do, you can linearize this equation for small phase differences. And then it's analytically solvable equation, because equation for pendulum with a damping is well-known equation in physics. And then you know that you can have certain free regimes of solution, very small damping, very big damping, and critical damping. So you have three regimes of the solution that goes naturally. So they are present. Can you go down a little bit? Yeah. All right. So this is this analogy, and
okay.
Yeah. So and perhaps do you have ability to write down the equations? Okay. So can you come to your slides, because I have seen that you have this ability to write it down.
Yeah, sure.
Yeah. Can you come to? So can you copy these equations that has three terms? that you write it down. Can you copy it on next slide, and then we.
Okay. So I will. Okay, it's here. This equation, yes.
No. The one which you have already written by your own hands. I prefer this one. No, from your presentation, not now.
Okay, sure. So
at the very beginning you did it.
Okay, I will write it.
Because I want to mention about two regimes of the solution.
Okay. So the equation was I is equal to I0 sine phi plus C derivative of V over time plus
Yes, but can you write down everything in terms of phase? So just that's okay. Just copy this equation and write under the instead of dv over dt. Just replace. Okay, and voltage is what? Voltage is what's the relation of voltage with phase difference?
The relation of voltage and phase difference was,
yes.
I mean, the rate of change of the phase was proportional to the voltage. Sorry, what?
Yes, this was AC Josephson effect, so-called, but just you need to express it now.
Okay. So
yeah, I hope that previous equations could be preserved because we need both of them. Yeah.
Okay, so plus okay. Okay, so voltage is, of course, phi 0.
And yeah, phi 0 is a magnetic flux, but that's also expression in terms of current to E. What's the expression?
Yeah, sure. So it times divided by 2 pi. So if we divide by 2 pi, it's simply like this. Well, okay. So voltage is plus C. Okay, I forgot about C. C d square phi dt squared, and this is plus.
Maybe you can shift this equation on this voltage on the very left upper left the right upper. I'm sorry.
Okay, I hope so. I hope I can do it.
Okay, so anyway.
H squared to 2e times r d.
Very well, but on the very left, just write the current as a function of time on the very left side. Just place time index to j. Left, go to left, very left of the yes.
Okay.
Just write down time index, whatever j as function of t.
J or y?
Yeah,
or I.
It's fine. All right. So this is the type of equation you are dealing with, and now You know that there are two types of Josephson junction: tunneling Josephson junction and weak links. So the tunneling of Josephson junction, maybe you can sketch it on the right side. So two superconductors sandwiched by insulator, just
okay,
down.
on the right side, whatever.
Yeah, you have some empty space, right, on the right side. I thought, can you make it a little bit topper on the toppers? Because there are two cases, so I will ask you for two circuits. So can you shift it upper?
Okay. It's not as easy. I would have to redraw it probably.
No. Oh, okay, well.
Okay.
Okay, so just, and then there is constriction, which is like narrowing between two superconductors. So there is no barrier in between, but there is a kind of narrowing, like see on my fingers. It's a narrowing, something like that. So can you write it down?
Okay. Okay. So this is simply like this.
Yes, exactly. And then write it down: weak link Josephson junction, and on very top of it, write weak link Josephson junction.
Weak link, like this?
Weak link.
Weak link.
K is weak hyphen link.
Okay, yeah, okay.
Weak link Josephson junction. Yes, weak link, yes, JJ, and below tunneling JJ. And what's the key difference between them? Well, there is a dominance of existence of capacitance in tunneling Josephson junction. So in the bracket, you can write that capacitance is bigger than 0. Just write it on the right, in the bracket, on the right side of tunneling Josephson junction word.
Here we have capacitance.
So capacitance, which is bigger than 0. And for a weak link, write it, capacitance is set to 0. Just write it. Because you have the same material, so there is no sandwich. It's just narrowing. So in both cases, you can recognize that resistance is non-zero in both cases. But what is, and now you have two versions of the same equation that you have written. So please, and also please denote weak link as a case 1, like 1, and tunneling Josephson junction as case 2. So just write it.
Okay.
Case 2.
Actually, I mean, here we have plus.
So in one case you drop capacitance. In one case, so there is no capacitance. So it gives you a very big simplification of the equation and its solutions.
Yes.
Yes, very well. And then write it to the second case.
Okay,
and actually, you can solve those two equations. In any case, the solutions of this equation is supposed to give you quite different, dramatically different current voltage characteristics. So I suggest you copy the weak link equation and go to next page and then try to solve it, assuming that J on the left side is just constant. So please,
okay.
yeah, and try to determine the current voltage characteristics for that equation.
I wish I could simply paste it.
But you can retype it just by remembering, right? You can retype it.
Okay.
You are impressive. I'm impressed with your
Nice to hear
ability
that.
to on the spot respond to commands, copy paste. Remember, I mean, you are unbelievable. No, I mean, I mean it. I'm not.
Radoslaw is doing his second engineering degree. He already has one engineering degree, so he's quite capable person. That's why I believe in him.
Of course, I would be maximally impressed, but I don't know what software you are using now. If because there are softwares that you can type, you can use LaTeX to basically type your equations, and they will come up like almost like in typeset format. But I don't know. I know PowerPoint had an editor for LaTeX, so you can type LaTeX into PowerPoint. But I don't know if this one. This is an HTML, right? This is
Yeah, I would be really good to the name of this software. That would be really cool to know.
Okay, we try to provide you the name. Maybe you can provide the name of the software on the chat, Radoslaw.
Okay. So this was the case for weak link. Link. Okay, so I rewrote it.
Okay, and then just J as on the left side, just J is equal J of as function of T. So it's a J. On the left side is just J, let's say, in first, because we will search. So what you need to find out, what's the time dependence of phase here. So, okay, and then, so what you need to do next? So you need to have time on one side and the phase on another side. So you have to make clever steps. So I suggest J minus J0 sine theta is equal to just go on.
J minus.
Just J0 times sinus theta is equal to.
Okay, sure. Is equal to this quantity.
And then I suggest you divide both sides by J minus J0 and multiply by dt, both sides. So on the left side, it will be dt.
Maybe I would like to have this on one side. So maybe.
Yeah. Just make dt on the left side. So, okay, let's at first divide both sides by J minus J0 sine theta, the sine phi. Just divide both of them.
Okay, so here we would have H2 by this is equal to 1.
You miss sine theta, sine phi. And just
yes, but does it really help us? I think
okay, it's fine. And now you okay, just type J0 times sine phase difference, and now you multiply both sides by dt. So go to next stage, multiply both sides by dt. So you will have dt on the right side.
Okay, so is equal to the theta, and all of this is divided by 1 minus.
Very good.
More or less.
And now you need to integrate both sides. So integrate it. So on the left side, you get t minus t0.
Okay, so but here we have in denominator.
Doesn't matter. I mean, it's just integrate of certain type, integral of certain type. So yeah, it's just I suggest you just integrate. So you have t minus t0 on the left side, right? T minus t0.
Yeah, I mean, if we suppose that we count from 0, then we can skip. Okay, I will write it explicitly. So minus t0.
Okay. And then you can factorize the whole expression by this constant h bar over 2er. So just write it from very beginning, h bar over this ratio, right? Times integral from phi 0 to phi, maybe phi 0 to phi 1, let's say phi 0 to phi 1. And then this expression 1 d phi over right. So because the purpose of your okay, so what will be the easiest case? I would say if you pre-assume that your phase difference is very small, then sign phase difference is sign phi is phi, right? So perhaps can you copy this integral to the next slide so we can proceed further?
Okay, I will have to remove that and copy something. If I manage to copy it, if not, I will simply rewrite it, I guess. It's be much. Okay, so here's the factor. Here's the integral from phi 0 to phi 1 to 1 over I. Okay, so.
Yeah, but you're supposed not to write sign anymore, just for the sake of simplicity. You just
Theta.
It's okay. You can do it in the next. You can do the small phase difference approximation and then replace sine phi with phi.
Okay.
Do it in the next space. Like do like in the extra. Do like kind of like a phi smaller than 1, whatever, so people can understand that you're making an approximation.
Yeah, and also please factorize the denominator by j. So just write. So please factorize this denominator by j. So h bar over 2i r j. You know what I mean? It's just I try to simplify things. Yeah. Okay.
Okay. So I will rewrite this small phase approximation. So we have 1 over. Okay, the phi, of course.
Because if you make this approximation, yes, and now you can okay, I was hoping that so you can make a variable you can define new variable phi 1 is equal to j minus j0 times phi. So make a new variable phi 1
equals to
j minus j0 times phi.
Okay.
Right? And then d phi1 is equal to what? I just want you to compute this integral because it will be simple integral, right? Yeah, but yes. Okay.
Okay, and sure. So the d phi1 d phi is equal to minus I is 0, minus I 0. So d phi is equal to minus
Yeah, sounds good. Right. So you
yeah,
need
okay.
yes.
So now I have to replace this by minus. So I can write it even here, minus I 0. Is it visible or not? It's maybe I can make it a bit more legible. I 0 here, and okay.
And then just compute this integral. It should be. Yes. I believe you. Yes. Is this? I think it's. What did happen to minus? Minus was already included. Okay.
Yeah, it's included here. Yes.
So just compute this integral. It's quite elementary integral. Okay. If you can compute it, I would appreciate it.
Yeah. Sure. Okay. 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 ln phi, but it has to be from. We have to change the limits of this integral because now phi 1 would be confusing. Whatever, let's say phi e phi f, like initial final. So okay, so it's simply minus this thing times natural logarithm of the ratio. Is it?
Yes, everything is fine. And now, what you need to do is you need to put both to apply exponential function to both sides. So on the left side you have e to the power.
Okay.
Yeah. Okay. Maybe at first at first just multiply both sides by 2 ERJ0 over H bar minus. Multiply both sides.
Okay.
Maybe on next slide or whatever.
Yes. So okay, this slide is taken. Maybe I can add slides.
Before you move, can you also copy and put in the chat that German link, which was the source of the previous schematic that you showed in your slides?
Of course I can. Yes. Maybe maybe I will do that right after this derivation because
Okay.
Yeah, I'm afraid that it will disappear. So can I edit it while presenting it? That would be
I can do it because I can do it for a person that was asking this question. Sure, I have some
okay, perfect. Okay.
So
Luckily,
would recommend.
luckily, all of that is recorded, so I can just erase it, and it will be on the recording. Okay.
Also to save you some editing, either you have to adjust your t minus t0. If you're going to use phi initial, phi final, it would be better to use t final, t initial instead of t minus t0.
Yeah, or just
it-
delta t, or just delta t is also fine, right? Delta t.
Delta t would be the most economical
yeah,
one.
okay.
Yes.
So if it simplifies the notation, then yeah, why not delta t? So now minus 2e ri0 by divided by h bar delta t is equal to this natural logarithm. It's f, sorry, and initial. Then we take I mean, yeah, we just take like insert it into the exponential function. So now we have is equal to this ratio. Okay. So
I think you need to erase the exponential under the t in your middle line, potential of the entire thing.
Yeah. So
but
just
it's the same thing. I mean,
no.
You need to erase the
sorry, okay,
exponential
so it's,
under the delta t.
Yeah,
yeah,
just please erase exponential. Yes, now it's fine. Yeah.
Definitely. So yes, this is yeah. Okay, so this is all this thing to the power delta t, and
then what's
now
the
we can
final? Okay, so what's the final conclusion? What's the final phase is related to?
final phase is related to the initial phase, like this. Okay.
Yes, it is. And so what does it mean? That after a very long time, final phase is what?
So in the limit where when t tends to infinity, then final phase would fade out to 0, I guess.
Yes.
Like if it's
Yes. It's also this is there is analogy because here is this mass. There is nice case of ping pong ball and big stream of air from vacuum cleaner or whatever. So basically the current situation which is here almost pre-assumes mass zero of this pendulum case, right? So in that sense, the system responds very quickly to so adapts. So, but the question which I try to also answer is, let's say, what's the possible relation between voltage and current from in that regime? What would you say? What's current voltage characteristics? You know from theory of Josephson junctions two types of current voltage characteristics. Can you draw them and can you somehow justify them?
I think I would need some reminder.
Yeah, go ahead.
Okay, so
I can give a hint. There are two different current voltage characteristics specific for either for weak link regime, so two superconductors sandwiched by insulator, or for a constriction regime when you have narrowing. So they are completely different. So can you draw them, a scheme of them?
Um, well, I don't remember them.
Okay, so please check them. Maybe now it's good time to check it.
Okay, so
Josephson junction current voltage characteristics. You can type it something like that.
okay, so I can Google it here.
Yes, so this is one type. So this type, which you see now, it's for a weak link regime. It's high nonlinear, weak link
Okay.
regime, this one. Maybe you can copy it or place it. And,
okay, so I can simply draw it here.
And this one, which is, and another one which is used for rapid single quantum flux electronics is tunneling regime. Okay, so this is no, but this
is weak.
Correct, because it is you have to shift. This is antisymmetric function. So this line is on the OX. You need to shift it.
Yeah, okay. It passes through 0. I get it. Okay.
And also you need to shift it down towards, because to my minus values that are present.
Yeah, sure. I get that. I will simply draw the axis here and here.
Yeah. So this is tunneling regime, weak link. Yes, this is weak link, right? This is a regime under your considerations from equations point of view, because it's simpler.
Okay.
And then the second one, check. And the second one is like under is yes on the very right side with this continuity. So let's say it's on go to the right side with this. Okay, there is yes. Click this.
This one, yes.
Yes, so this is another one. Yeah.
Okay.
So please type it.
So this one, okay, I will again erase the axis. So this one was like this. Okay. Yeah, okay. So
but there is
remember
big,
this graph.
There is big peak in which you missed. Big peak around voltage set to 0. Just check. You missed big peak.
Yes, sure.
Maybe you can use different color or whatever. I don't know. It's up to you. But
okay, sure. So it was like here, then it was like
yeah, right. And basically, from your assumptions, from your considerations, you have seen that phases stabilizes for a weak link, right? For long times, right?
Yes.
As you pointed out. But so for both current voltage characteristics, what is very prominent feature is that there is current flow under the case of 0 voltage, which is so both current voltage characteristics has this feature. Current flow with 0 voltage drop across Josephson junction, which also is related to the fact that you can have no dissipation or the flow of charge without dissipation. yeah, and also, but there is also second consequence of this model. Second consequence of this model is, can you go to previous slide? That the second
no, not this one. This one.
No, before. No, there was this case of, yes, the free. There was this with, yes, this one. So you
Okay.
have this. I'm talking about the second line. Then there are three terms in this differential equation. So here you have the cycle of phase difference evolution with time. So you have hysteresis. Which you can induce. So, for example, you can prefix some term like voltage, and then you will see how this, or you can prefix current flowing, and then you will see what's the phase dynamics with time. So then you will move across this current voltage characteristics, which you have written down. So also the secondary equation you can solve with this pre-assumption of small phase difference when you linearize this equation, and then you can find out certain solutions. So I recommend you to do it maybe for next time, so you can simply have more justified view of this current voltage characteristics that we have pointed out today.
Okay, so I write it down.
So are we have any more question from Janice or anybody else to the given presentation? All right, I guess Radoslaw, is it all from your side?
Yes, it is. Thank you for your attention.
I suggest we continue next week at the same time. Yes, next week I will point out this washboard potential concept will be derived, and nevertheless this conclusions from today will be important for next week considerations. So if there are no more questions, I thank you everybody for your presence, and hopefully see you next week. Thank you. Bye bye.
Dziękuję bardzo.
Dziękuję.
Dziękuję również.